Good afternoon, everyone. Welcome to me and my group's presentation on the Logistic Map. So the Logistic Map is a function which is used to map the growth of a population from one year to the next. It's given by this formula where xn is the population in the current year, xn plus 1 is the population in the following year, and x must be within 0 and 1, 0 being extinct and 1 being the maximum possible population. The constant a is the fertility constant, and it must satisfy the parameter 0 to 4, 0 being a very low fertility and 4 being a very high fertility.
The Logistic Map was named in 1844 by a man named Pierre-François Verhulst after he was studying it in relation to population growth. Poincaré, who has a room within the school, was the first mathematician to discover chaos after discovering unpredictabilities in his work in the 1880s, causing him to create Poincaré plots, which we will discover later. Newman, who also has a room within our math school, suggested using the logistic map of x to the n minus 1 equals 4xn times by 1 minus xn in 1947. Edward Lorenz, also described as the father of chaos, was the first to define chaos after predicting the weather in 1961. He described chaos as when the present determines the future, but the approximate present does not approximately determine the future.
So to show you how the logistic map works, we can use an example population of animals, and we're going to be using elk, which are a large species of deer. And in all the scenarios we're about to do, the starting population of the elk will be 0.5.
Imagine a population of elk. Biologists want to measure how his population will change in the future. Let's say that the elk have a low fertility rate because it has been a harsh winter and there is not enough food. In this case, A, the fertility rate, will equal 0.8, and as you can see after a couple of iterations, the population goes from 0.5 to 0.2 to 0.1. If we continue this, it will just get smaller and smaller and smaller, and by iteration 12, the elk will have gone extinct.
In scenario 2, we have set the fertility of the elk is fairly ordinary because there is sufficient amount of food and the population of wolves is not too high. In this scenario, we have set A to be 1.2. As you can see on the graph, the value of the population starts to converge to 1.8, which shows the population has reached a constant state.
In scenario 3, the fertility constant is 3.2, which is relatively high. Again, the starting population is 0.5. Through the iteration, we can see the population converges to two values, 0.8 and around 0.5. Well, the reason for this is because the elk's population fertility rate is so high that the competition for resources is so great that there is a dip in population, but then that bounces back again because there's enough resources to sustain the population.
In scenario 4, the fertility rate is extremely high. And at this point, it stops going between two values or four values or something, and the population becomes chaotic and unpredictable. So you could think of this as sort of cycling between an infinite number of values.
So the behaviour of the logistic map can be modelled using a bifurcation diagram. And this shows the effect of altering the fertility on the population value. So as you can see, when A is between 0 and 1, the population stays on 0, meaning the fertility is not high enough and the population goes extinct. When A is between 1 and 3, we see the population reach a stable value, shown by this one line. And as A is beyond 3 and less than 3.6, we see this period doubling effect where the population settles on two values and then 4 and then 8 and then 16, quicker and quicker and quicker until at about A equals 3.6, we see the onset of chaos where the population does not settle on any values that we can predict.
Chaos is a branch of mathematics concerned with the non-linear and unpredictable. It teaches us to expect the unexpected. Chaos theory is the concept that small changes in extremely sensitive initial conditions can have huge consequences later on. This is also known as the butterfly effect and can be seen in weather and traffic systems. Reiterative structures are another feature of chaotic functions. In the logistic map, if we zoom in on the chaotic area, we can see an identical copy of the original bifurcation diagram. This is also present in fractals and other chaotic functions.
So in our project, we were tasked with modeling the logistic map function. So here we used Excel, and we plotted different fertility rates and their effect on the population. Still me. So Feigenbaum's first constant. So how do we get Feigenbaum's constant? So what we do is we take the distance between one split to the next, A. Then we take the distance between the next split, B. Now if we divide A by B, we get this constant that converges to around 4.7. So this is possibly irrational, and it was discovered by Mitchell Feigenbaum. What's really special about this constant is that it's universal for all maps that behave chaotically.
And so because it's universal, we can see it in something that you possibly have seen before, the Mandelbrot set, which is fairly famous for being a fractal. But because it has this iterative formula, Zn plus 1 equals Zn squared plus Z0, and it's the set of numbers for which that converges, we see, so it's basically a bifurcation diagram, which means that this Feigenbaum's constant pops up in here. As you can see, by scaling and moving it around a bit, we can line up points like that.
A cobweb plot can show how the population increases year by year. It is used to demonstrate the behaviour of the iterated function. We use the y equals x graph and the graph of your function to be able to make these cobweb plots. You start with your beginning value of x and plot from the x-axis up to your function, where you then plot horizontally until you get to the y equals x line. At this point, you repeat this process again with the new value of x. These create the cobwebs, which will spiral about the point where the y equals x line and the function graph will intersect. If the function converges to a value at the point of intersection, the x-coordinate will be the limit of the function.
Poincaré plots are interesting. These were created by a man named Henri Poincaré. The main function of these are to determine randomness from chaos by showing a one-dimensional set of data in a higher dimensional set space, so these would be 2 dimensions. These are created by finding the first and second iterations or points of a function and plotting them on the x and y axis respectively, and then the second and third iterations or points of a function, and then third and fourth, etc. If this creates a pattern, as is shown in this, then chaos is present rather than absolute randomness. If there is no pattern, then there is obviously randomness. This can be done in any number of dimension. As you can see, here is a 3D scale. The different rainbow colours represent different points from r equals 3.6 to r equals 4.0, as we discovered earlier.
So we'd like to say thank you to Andrew Gilbert and Louise Haggett. If you have any questions, please see our poster, and thank you for listening.